what I would say, just to begin with, is my career has been very much in the world of propulsion and power, spanning many years, as you might see by this carefully aerodynamic profile that you can see across here, spread across a number of continents around the world, looking at some very exciting technology. But what I would say is never has there been such an exciting time in the world of propulsion and power as we've talked about already this morning. So we're going to unpack that a little bit more this afternoon, and I know you're all enthusiastic and excited about what we're doing in the world of propulsion and power. So without any further ado, just a quick reminder there about Slido. So you can find, if you don't have the app, you can look at it on the website as well. You can download pop your questions in there, and we'll be coming on to that a little bit later. It's very much meant to be an interactive session. It's your opportunity. You've heard people talking a lot this morning. This is your opportunity to talk to us and ask questions and interact with the panel, who I'll introduce very shortly. So, first of all, I'll start off talking about what we classified in our strategy as really the targets and the drivers. So what is it that's really driving the world of propulsion and power? So we have, first of all, the world of, in terms of targets, we've specified some very challenging targets around, first of all, CO2, which aligns very carefully with the direction that we talked about this morning in terms of CO2, in terms of sustainability, I should say. And that quite clearly is an agenda that the aerospace industry, certainly in terms of propulsion, has been on for quite some time. This is about continuing to evolve on that journey. The next one that's on there is around NOx, so the nitrous oxides. So how can we further reduce our nitrous oxides emissions? And then third of all is around noise. So all of those three things are key discriminators around propulsion systems of the future. So, but in terms of our real drivers around this whole world of propulsion, we want to continue to improve safety as the fleet continues to grow in terms of new vehicles approaching. We want to be continuing to drive levels of safety in proportion to what's actually happening across the whole industry. In addition to that, we want to reduce cost. So that's clearly an action in terms of competitiveness, whether it's competitiveness in terms of providing the equipment or reducing cost in terms of operating. They're all critical factors in terms of competitiveness. The next one is about energy efficiency. So propulsion has a huge role to play in the world of energy efficiency. Regardless of the type of propulsion system we're talking about, lots and lots of different types of energy reduction that we can think about, and we're going to explore some of those through this afternoon. The next one is about protecting the environment, which again reflects back on our particular targets that we've specified. Meeting our operational needs and flexibility. So we want to make sure that if we introduce a new propulsion system, that we actually, from an airline perspective, in terms of being able to actually utilize that air vehicle, they can actually operate it in a range of different environments, range of different missions. So you've got some flexibility, but you've got some good turnaround times and things like that as well. So they're all clearly quite important. And then the last one is about passenger experience. So we want to think about how can we continue to improve or reduce levels of noise for occupants within the air vehicle. So they're all factors that play into our thinking about what might be of interest. So moving on a little bit. So let's have a look at our key priorities. So we have three priorities that we're going to explore this afternoon. So the first one is about ultra-high bypass ratio turbofan engines. We're going to dig into that a little bit more in a short moment, and then we'll expose each of these through each of our panel members. So ultra-high bypass ratio turbofan engines is number one. Number two is around the world of hybrid electric propulsion systems. So how can we, this is clearly something that's quite disruptive in our market, so how can we create commercially viable hybrid propulsion systems of the future? And third of all is all electric, and fuel cell type systems. So very disruptive fuel propulsion systems of the future. So those three things that you can see on the screen there are three priorities for propulsion and power. Really, really quite straightforward, quite challenging. So let's unpack each one of those in turn. So if we have a look at ultra-high bypass ratio turbofan engines, it encompasses lots of things, and I'm not going to go into an enormous amount of detail on all of that. And I should say also that none of our panel will have time to go into detail on these aspects either, because we are literally doing tasters to provoke you into asking questions. But certainly, ultra-high bypass ratio turbofan engines bring with them whole new challenges around the LP system, around reducing weight and about actually having highly integrated systems and highly integrated systems that integrate with the airframe. So that's really, really important. The second priority, or second option that we've got in there, or not even an option, but a second factor for ultra-high bypass ratio turbofan engines, is really about driving down fuel burn and CO2 emissions. So a lot of that is through thinking about advanced materials, a lot about thinking about other novel technologies which drive the core of gas turbines as we know them today, but really taking these and evolving these way beyond what we can see in the market today. Third on there is something around combustion, and these are just examples that I've picked from the strategy. You can find more of that in the document as you read that today. So lean burn combustion is one mechanism for reducing some of those emissions that I mentioned earlier in terms of our targets. So you might want to be interested in some of that. And then the last one is we need to be thinking about alternative fuels. So Paul Stein this morning, Paul Stein from Rolls-Royce, when he was talking about his view of, or the Rolls-Royce view, I should say, of the future, it certainly encompassed the world of alternative fuels. And we certainly need to be thinking about that and factoring that into what does that mean and how does that impact on ultra-high bypass ratio turbofan engines of the future. So that was really a quick canter through ultra-high bypass ratio turbofan engines. I think the one takeaway that I would say on that is this is very much not purely about Rolls-Royce. This is about really broadening from a UK perspective that whole supply chain in terms of innovation, disruption, and how to actually deliver some of that key technology in the future. So this is a big opportunity for people to start thinking about how to engage with ATI and other folk around the UK to actually start to bring in some compelling technologies. So a great opportunity. So that was all I was going to say about ultra-high bypass ratio turbofan engines. I'm now going to go on to our hybrid gas turbine electric systems. So in our strategy, you'll find a number of areas of interest. So one of those quite clearly is about the electrical power systems that you need for some of these hybrid systems. So we're talking about pretty significant power levels. We're talking about typically megawatt level systems. So they're pretty challenging, both in terms of delivering those, operating those, and actually how we sustain that environment in terms of delivering hybrid systems of the future. So quite a few challenges around that. We can unpack a few of those this afternoon on a specific case point as well. Thermal management is a huge one. So thermal management sits everywhere. This one specifically talked about in terms of hybrid electric, but you could see thermal management in every form of propulsion today as being a key challenge. So why is it so different for hybrid systems, hybrid propulsion systems? One of our challenges really is that we're actually now, even if we have hugely efficient electrical power system, electrical drives, then the levels of power that we're talking about, even if they're 98% efficient or 97% efficient, that 2 or 3% of inefficiency is quite a lot of heat that somehow we need to dissipate and manage around the air vehicle. And we've got significant challenges in terms of how we do that. We also need to think about how that integrates with some of the gas turbine, if we're thinking about a true integrated gas turbine hybrid system. So all of that thermal management doesn't come for free. It's extra equipment, extra plant equipment that's required on the air vehicle. And one of the challenges in terms of competitiveness is how we deliver thermal management solutions, which are competitive in terms of low weight, low complexity, but high impact in terms of delivering. Third on there is about high voltage. So I mentioned high power. So one of our challenges really in terms of delivering high power propulsion systems is that we really do need to think about increasing the voltage levels. And so you'll see that mentioned in many of the demonstrator programs today, several kilovolts of power, power systems that are being talked about today. That brings with it all sorts of challenges around how do these high voltage systems actually operate in an airborne environment? And the answer is, we clearly understand some of the risks, but we don't know. So we need to do some demonstration work to better understand some of that activity. So quite important. And the last one is about really thinking about how do you integrate a hybrid system together with an engine? How do you do that in integration to come up with a successful solution, a successful and viable solution in terms of an integrated hybrid electric solution? There's multiple different ways that you can think about this, but integration is going to be key on this. So no one single technology is the make or break for hybrid propulsion. It's really about integration and about how the successful products of the future are going to be delivered by people who have taken on that integration challenge and really thought about how to deliver integration in those products. So that was my quick canter through gas turbine hybrid electric solutions. So on to our third one, which is about all electric and fuel cell systems. So we've got to mention batteries, of course. And of course, everybody says, well, batteries just aren't good enough for what we need. Well, the question is, what do we need? And for some of the short-range vehicles that we're talking about, and we've had mention of earlier this morning, batteries actually are quite viable for some applications. There are some challenges around battery systems today. Battery systems today are clearly really being developed for other sectors, and those other sectors have very different requirements. So how can the aerospace industry help to influence some of those requirements around batteries of the future? There is a lot of activity in the UK, specifically through the ISCF Faraday Challenge, which is driving a lot of research in the UK on batteries. The ATI are very integrated into that thinking. They're trying to drive a lot more thinking around aerospace. And there is actually quite a degree of activity right now around setting some specific requirements for the world of aerospace, which help to drive even more challenging battery capability in the UK. So that could be an interesting area. The next one is around fuel cells. So fuel cells, people are going to be talking a little bit about fuel cells this afternoon. We may anticipate hearing even more about that as time goes by, as people better understand where some of the opportunities might be on fuel cell systems. Airborne fuel cell systems are quite disruptive, quite innovative. So it really does make us think a little bit differently about what we want to do in terms of some of these all-electric sort of fuel cell systems of the future. And many organisations around the globe right now are exploring opportunities around fuel cell systems. The last one, third one I should say, that's on there is about for our all-electric systems, we want our power electronics, machines and drives to be very high efficiency, high power density. So if we're going to really be delivering propulsion systems through electric drives, then, and the same would apply equally to the hybrid ones that I just talked about, then we really, really do want to see lightweight solutions, highly integrated, well packaged, that really are competitive with what we can see relative to today's propulsion mechanisms. And then the fourth one that I have pulled out on there again is about integration. So electric propulsion integration looks and feels very different to what we do today with gas turbines. We're connecting things electrically. We've got some big, potentially big wires, big cables distributing around the aeroplane, doing very different architectures to what we might have around us today. how can we integrate some of those? We might want to integrate some of that into the structure. We might want to think about alternative solutions, really, about how we can do more of that capability going forward. So that was really our world of all-electric systems and fuel cells. So just to kind of whet your appetite. So the final slide I've got for you here is just very quickly. Simon flashed up this morning that there were some roadmaps in our strategy document. You're not going to be able to read this, but there is a roadmap for the world of propulsion and power. It's a framework. It's the beginning of a roadmap, and it's very much meant to be a provocative engagement with the aerospace sector around what you think should be coming along in the future for propulsion and power. So, you know, this is certainly sets out some of those things that I mentioned there in terms of targets and drivers. It starts to identify some of the key areas, some of the key technologies which might be delivered across the next few years. So quite an interesting opportunity for you to digest in our new strategy. So moving on to really the format of today. So our panel for today. So I've done enough talking for now. So we'll start off with our panel for today. So we've got quite a varied panel for you today. So we have Jackie Wildhaber from Rolls-Royce. We have Jenny Kavanagh from Cranfield Aerospace Solutions, and we have Julian Renz from Zero Avia. So and they're all going to bring some very different aspects to help you think differently about the future of propulsion. Very, very different to what we would have been talking about some years ago if we were really focusing on propulsion. So do get to welcome each of our panel members as they come along. They're going to give you, each of them are going to give you a very brief 5-minute taster around their area. And what we've asked them to do is to really each of them to focus on one aspect, one of our key priorities, whether it's UHPR, turbofans, hybrid electric or all electric. We're going to get some slightly different context-driven views around each of those. So without any further ado, I'll hand over to Jackie.
Thank you, Mark. So, good afternoon. I'm Jackie Wildhaber from Rolls-Royce. I work in the Aerospace R&T team, so looking across our portfolio of technology for a range of products. So, as Mark said, I'm here to try and provide a little bit more information about the UHPR priority. Earlier today, we've heard quite a bit about the sustainability, and Mark's shared with us the environmental targets that we're working to. So this is a slightly different version of a chart you'll have seen earlier today from Paul Stein, talking about the three pillars of the Rolls-Royce environmental strategy for aviation. So just to quickly reiterate it, we've got sustainable aviation fuels. Paul covered that in some detail this morning. Well, there's another session, I think, tomorrow on the environment where there'll be some more discussion on that, so I won't major on that. Second strand is the electrification of aviation. And I think just pause there for a moment because there's a lot of excitement about electrification. And some people say, well, why do we still need to work on the gas turbine when we're going electric? So, as we've alluded to a few times, the degree of electrification really does depend on that you can make viable. Depends on where you're how far you're trying to go, how much you're trying to carry, and how fast you want to go. If we move to less energy dense fuels or energy storage, we're going to reduce the range that we can travel. You can then increase how much payload you have for that energy storage, but that will reduce your revenue earning payload, which is not going to be attractive to the end customers. You could resize your aircraft, but that isn't particularly feasible for the large end of the market, possible for the small end, which is why you'll have heard us say in various of the talks about how you can see the opportunities in the small end, but the larger end, the medium, long-range aircraft, large aircraft will continue to need a gas turbine. So hence, the bit that I want to focus on, which is continuing to evolve the gas turbine. So the good news is there is opportunity here. So there's two approaches, two axes that we can work on. One is that of improving the thermal efficiency. So by pushing the cycle in terms of pressure ratio or temperatures in the cycle, improving the component efficiencies. And if I can get the pointer to work, I'm struggling a bit with, apologies. So that was on the left-hand axis coming down there, as we improve efficiency. You'll sort of see a sort of green hash sort of box, and that's sort of where we start to hit one of the limits around stoichiometric combustion. But there are other types of combustion which could push you a bit further and ultimately be limited by the efficiency of components. The other axis we can work on is that of propulsive efficiency. So we can, that's a measure of how much useful thrust can be generated by a given power. It's to do with the efficiency of conversion, the difference between the exhaust velocity and flight velocity. So you get improvements on that axis through reducing fan pressure ratio and increasing the bypass pressure ratio. The limits there, certainly with a conventional gas turbine, fan diameter, you reach the point where you can't fit the thing under a wing. And ultimately as well, there's the component efficiencies. You can drive further along that direction as you start to move into distributed solutions. But so when we're talking about the UHBR, the ultra-high bypass ratio turbofan, what we're doing is we're both improving propulsive efficiency by increasing the bypass ratio, and we are improving the thermal efficiency. We're going smaller, hotter, more efficient cool. So the Rolls-Royce incarnation of this is the Ultrafan. So this chart here was a quick summary of some of the key technologies. So in the Ultrafan, we're talking about having a gearbox driven by a high-speed IP turbine, and that's then driving a low-speed fan. Won't have time to go through all of these technologies. You've got to bring those together and integrate them. So the key aspect is the demonstrator program, which is approaching its critical design review and looking to run first engine in 2021. We can see here, for example, challenges around the power gearbox. We've talked about the duty that's having to do. So thermal management is also an issue here, generating a lot of heat for that duty. The size of the fan, we need to have lightweight fan system, so that's bringing in composites. The diameter brings in, you need efficient propulsion packaging in the cell to bring down the diameter. What else to bring out? And I'll bring out lean burn combustion as well. So, on the composite fan system, number of engine and rig tests run to date, power gearbox rigs been running on power and attitude rigs to bring that technology forward. Lean burn combustion is run in the core demonstrator and also in a Trent-based demonstrator, and we're working towards flight. And I'm being looked at, so I think I'm out of time. Yes. So apologies, I didn't manage to touch all that, but thank you for listening.
So I'll just introduce Jenny Kavanagh from Cranfield Aerospace Solutions.
Hello, my name is Jenny Kavanagh. I'm Head of Airborne Systems at Cranfield Aerospace Solutions. If the UK aerospace industry is going to capitalise on the opportunities presented to us by electric aviation, we must get ourselves past a series of interesting engineering projects and get a product to market, thereby establishing a UK-based supply of certified electric motors, batteries, power systems and aircraft-level systems. And we at Cranfield believe that a hybrid electric solution is the route to do that. So I'm going to take you through some of the key considerations. I only have 5 minutes. And then a brief introduction to Project Fresson, which was officially announced at midnight. No, that's backwards. Hold it the right way around. Okay, so the first consideration is safety. So safety in aviation must be and is the heart of everything we do. And electric technology has in it certain inherent safety challenges. I think we're all very familiar with this sort of photograph from the automotive world. So, as Mark said, cracking thermal management is a key to getting any electric product into certifiable flight, because there is no lay-by at 15,000 feet. The second is certification, which is inextricably linked to safety, of course. Certifying any new technology for flight is difficult enough when the regulations exist and the safety cases are clear. Certifying a technology for which the regulations are still in flux is there slightly bit more challenging. So any product design that is going to succeed beyond flight demonstration and into full certification must have close liaison with airworthiness authorities and industry working groups to help inform and learn from the new regulations as well as comply with them. So the key to ensuring that a new development makes it to market is to recognise that its product is a system of systems. The solution goes beyond the subsystems, beyond the propulsion system, even beyond the aircraft system, into the wider environment. It's not enough just for the technology to work. It must do so while giving operators the flexibility that need to maintain an effective operation whilst also saving them money. The business case has to stack up or the product simply won't sell. This includes maintenance and through life support as well as product upgrades. And we must also consider the infrastructure required to serve electric aircraft, charging infrastructure, airport safety systems and energy logistics. Fourth is range. It's been mentioned a few times today. So electric aviation isn't a new dream. People have been dabbling with electric flight since at least the 1970s. The difference now, however, is that the state-of-the-art battery technology has now reached a performance level that makes electric flight of a 9-seat aircraft a reality. By our calculations, a converted 9-seat aircraft could probably fly about 20 minutes on full electric flight, which is fantastic for a technology demonstrator. It's not going to cut it for operators when they're looking at diversion requirements of 30 minutes plus. So to make it a practical reality, at least as a first step to full electric, you need to have a hybrid element to the design. The final consideration is time. If the UK is going to play a large part in the future of aviation, we need to be getting a product certified by the middle of next decade. Which brings me to Project Fresson. So we officially announced this at midnight. It was actually launched at the beginning of October. It is an ATI-funded project to convert a Brit-Norman Islander to hybrid electric power. It's a 2.5-year flying demonstrator project with a follow-on phase of certification, not funded by ATI, I must add, to reach full certification by 2024. The product will be an OEM-approved STC that can be retrofitted to hundreds of Brit-Norman Islanders around the world. And to help us, 1 minute left, to help us with this very exciting project, we have a strong consortium of companies and institutions, as you can see, who are all experts in their field. And for those of you who aren't familiar with the Brit-Norman Islander, it's a much-loved British workhorse used around the globe by operators in isolated communities and island hopping applications. So by picking the Islander with this project, we're not only supporting the last British civil aircraft manufacturer, but we've also chosen an application that doesn't fight against the restrictions of the technology. Now, I've put on there, keep it simple. Obviously, I don't mean easy by that. What I mean by that is Cranfield Aerospace have over 20 years of experience in designing and certifying complex modification to aircraft. And we know full well that the less you change when you're attempting certification, the more straightforward the certification process is. And that's the reason why we've chosen to retrofit rather than trying to force a new airframe in at the same time. Acknowledging the system approach I talked about earlier, we've also been talking to several key stakeholders already, including operators via Brit-Norman, local governments, airports, and of course the airworthiness authorities. So finally, we believe that a hybrid electric solution is a means to achieve the ultimate goal of fully electric flight. We've therefore chosen an architecture that allows for all electric flight with the capability of extending range from a second energy source. In this way, it can benefit from future battery upgrades without redesigning the entire system, incrementally increasing that portion of electric flight as battery performance increases over time. And with this, Cranfield Aerospace Solutions, our partners, and our consortium members intend to enable the certification of UK-based components, subsystems, and platform-level systems that put the UK aerospace industry at the forefront of the third revolution of aviation. Thank you for listening.
Thank you very much, Jenny. And our third and final panellist is Julian Renz from Zero Avia.
All right. Hi, everyone. Thanks for the invitation, Mark. And I have the pleasure now, as a German, to explain to you how we make hydrogen work in aviation. Grazia was explaining earlier today that 50 years ago Airbus was formed. This is 80 years ago, I believe. I was not born then, as you might guess. But let me tell you why these 80 years actually have made time pass, that now we think that hydrogen electric propulsion can actually be the first real zero-emission aviation powertrain. And at Zero Avia, as you can see, we're working on that. The core of all this is really about being practical, right? Our core target as a startup is to get something on the market as fast as possible. And in order to do that, what we do is basically we think about three things a bit differently to make it practical. The first one is certification. So as Jenny already said, right, that is clearly a challenge. But you do make the challenge a little bit easier if you focus on the powertrain instead of on focusing on certifying an entirely new airframe. So in our discussions with the FAA, and now we're starting to ramp up these discussions as well with the UK CAA, and we're talking about a 3-year program as opposed to 5 to 7 years. Second, we're going after an existing market, right? So existing 10 to 20 seat airframes is something that operators fly around the world today, and we don't have to wait for the crazy stuff coming up and getting to market and actually getting public acceptance. We focus on the people that would use a Britten-Norman Islander or a Twin Otter today, and we focus on repowering those airframes instead of designing something completely new. And the last reason why I think we're practical is that we focus on an energy source that can actually deliver missions to these operators that they deem relevant. So instead of going after batteries for energy storage, which I think we've touched upon now, we think that hydrogen is a perfect means of energy storage on the aircraft to really deliver meaningful range and meaningful payload. If we bring all these three things together, what we think we can get to is by 2023 have a certified product, a certified powertrain on the market that can deliver 500-mile range, preserve the payload, and deliver significant operator savings. And if you want to see the difference to, for example, an all-electric powertrain, I made a little nice circle map around Birmingham, which unfortunately mainly gives you more water to cover. But just imagine putting that, I don't know, in Munich, where I come from, and all of a sudden you get a really attractive range that basically covers almost all of Europe. Of course, working with hydrogen does have its what about moments, right? There's no conversation that we're having where not somebody says, oh, but you work with hydrogen, what about this? Usually the first question is, oh, but what about the Hindenburg? I hope we've clarified that by now. What we do is, right, we start with a 300-mile flight next summer on a 6-seater aircraft. You can see it here flying on battery electric power in the US at the moment. We've recently announced an ATI grant that moves that program here to the UK, to Cranfield, where we work with Cranfield Aerospace and the university, and other partners as well, to actually make this 300-mile flight happen. And at the same time, we're looking to ramp up our ground tests for the scaled-up version of the powertrain. Basically, think about it as the same architecture of the powertrain, just scaled up 3 times to deliver the meaningful power for the 19-seater. And the 3 really core questions I usually get, and I hope that I kind of, can answer some of them now, and then, you can ask me more later, is 1, but is it really cost-effective? And we think, yes, it can be. You can deliver 40 to 50% of direct operating cost reductions to operators, just driven by better fuel and maintenance efforts. And you can actually become competitive with battery electric flying. Second question is, but does it scale up to larger aircraft? Does it actually work, from 0 to getting the first flight in place? And to both answers, I have to say yes. There is no physical limit that would limit you to, small aircraft. The basic system energy density of a hydrogen electric system can deliver similar things as jet fuel actually. And the economics do work as soon as you get roughly 2 flights a day from the infrastructure perspective. And last, just closing the loop on the safety aspect that you might have wondered about, opening up with the Hindenburg might not be a smart idea. It's actually, in our conversations with the FAA, the feedback that we have got so far is that we actually can really develop a safe system because you have reduced probability of failure. Those tanks that we're using are basically being shot at, and they're used in 10,000 cars across the world. And if there was a case of failure, the severity would likely be lower actually than with jet fuel today. And so I hope that this gives you a brief introduction to the topic of hydrogen electric flight. I'm happy to answer any questions now and look forward to the panel discussion. Thank you.
Thank you very much, Julian. So you've done very well. You've got many questions on Slido for us. We're not going to have time to do all of the questions, so I will select from these questions. Please do feel free to grab myself and the panelists later in the day or tomorrow, and do ask us more questions. So I'll start off with a general question for probably for each of our panel members, which is about a question that's asked about the approach of developing these new propulsion systems. So is the approach where we develop hybrid electric demonstrators, is that actually the most viable route to progress these technologies at the rate that we need? So who would like to answer that one first?
Well, that depends what you're doing with the technology demonstrator. If it's purely for the sake of demonstrating a technology that, yes, you can get an aircraft in the air, and then once you've done that, you then go back to having to ensure that you have an approach which is then going to go to certification, then that is going to take a long time. Our approach is that the technology demonstrator, which we'll have after 2.5 years, is a certifiable system, and so it will be a relatively short jump to certification. That's the plan. So it's actually on a trajectory of maturing the design as we're going through, as opposed to just trying to get a demonstrator in the air to show that technology works.
Okay. Any other panelists want to chip in on that one?
Well, I was just going to expand slightly in that my experience on demonstrators is that by actually going to the point where you are going to have to fly something and actually having to answer a lot of the integration questions, you flush those out earlier and you learn quicker than some more traditional type of approaches. So there's an awful lot that we don't know, and so actually by having to answer the big questions early on, we're actually flushing those out, and we'll get there. Will help us get there as efficiently as we can.
Okay.
And I think lastly, just to add to actually both points, it's also like we're in this as a startup. We don't have the money behind it that other companies do, clearly. So for us, it's also about de-risking the technology enough and demonstrating milestones so that we can, unlock additional funding going forward. So for us, it makes sense to demonstrate technology on something that is certifiable in its class, to work on that, but get there kind of as fast as possible. It's about the speed and the innovation in that.
And I'd just add from an ATI perspective, the role of a demonstrator is also a great means of bringing together people to actually work on that technology and accelerate that technology. So huge benefits from that. So thank you very much for that question. So our next question is a very specific question. Great question, but we probably don't know the answer to this. Do we know the optimum voltage level for future propulsion systems to minimise volume, mass, and maximise performance and reliability? I think the simple answer is
no.
I think that's why we're doing a little bit of work on this right now. Very good. So I'm just trying to cherry pick a few other different types of questions. So one question that came up, so this is probably one specifically for Jackie. This is around scalability of ultra-high bypass ratio engines. So it's a question about is the focus on the middle of the market, long-range aircraft? How does it work for lower thrust engines?
So I'm not sure the smallest size we're looking to go down to, but certainly, yeah, middle of the market and upwards, you would see this architecture fitting in. I think you start to get into some other interesting options when you go smaller, sort of linked to some of the other topics that we've talked about. So it's so there's certain aspects of this architecture which are quite heavy, so doesn't automatically scale to the smallest sizes. Yeah.
Okay. So probably a question here for Julian about hydrogen. So you might have partially answered this. What do you believe is the best way to store hydrogen on the aircraft, and more broadly around all types of future aircraft?
Yeah, the way that last little thing, that was an important part of the question, right? Because we think, hopefully that one point came through, right? What we're thinking about is how to get it to market as practical as possible. So what we do initially is focus on compressed gas storage, just because that is what reduces your infrastructure investment needs as well. It helps you just get it to the market faster ultimately. If you want to scale up the powertrain to higher power levels and ultimately also carrying more energy to go further or carry more passenger, at some point you will have to go to liquid hydrogen. What I quoted on liquid hydrogen system energy density becoming competitive with jet fuel, that you only get with liquid hydrogen. So the way we think about it is we can probably deliver as a next step, after the 20-seater, we can probably go into the 50 to 80 passenger market, potentially with compressed gas. It then really becomes a mission question of how far you want to go. The further you want to go, you will have to go to liquid hydrogen at some point, which makes the infrastructure more complex. But it's still something that's being done and being prototyped today. So I think that works as well.
Okay. Thank you. So the next question, we'll move into the world of batteries. So clearly I alluded to batteries are good enough for some short duration missions. I guess the question was, how can aerospace get the required volumes to interest our cell suppliers? Which is a really good question. So today's cell suppliers are very focused on not even the automotive sector, they're really about consumer battery delivery. So the automotive sector happens to benefit from something which is about good enough for automotive. For aerospace, it probably isn't. So the challenge really for the world of aerospace is how can we work with other sectors who have similar high-duty requirements and in some cases similar safety requirements to aerospace, and how can we really drive potentially a new supply chain around batteries for aerospace. And that's something that ATI is connecting with on the Faraday Challenge and some other sectors, so off-highway and some other sectors, to name but a few, certainly are interested in a more cohesive solution around battery cells of the future for aerospace. Anybody else got any more thoughts on that one?
Yeah, I'll add to that. I think it's a fantastic opportunity for UK industry. I mean, we pride ourselves on our innovation and our high-value design and manufacturing. And I actually think this is a great opportunity for the UK to create a relatively niche manufacturing cell manufacturing industry here that services those industries that don't need them in the millions and millions of cells. It's a great opportunity, and I think we should be working with those other industries as well, not just aerospace, that also need it.
And just to add to that, 'cause I think it's not only a question about batteries, right? It's also about electric motors, it's about inverters, it's about, in our case, it's about fuel cells, right? They don't originate from the aerospace industry. It's our job to get the manufacturing capabilities ready so they can be used in the aerospace industry. But you have to kind of bring those people in that know how to do really power-dense motors. I think we heard, I don't know who was in the pitching session just before, but people from the automotive motorsport industry, know how to do high power density electric motors and get them to work in aerospace. It's a good way to start.
Very good. Thank you. So we've probably got time for another couple of questions. So going to go in a slightly different direction here, which is about really about what I mentioned in terms of operational needs and flexibility. So what are the consequences of moving to electric power on aircraft turnaround time, and what are the opportunities for support services? So it's quite a broad question, that. Any thoughts on that one?
I mean, I can start, because it is clearly, right, the operational requirements is one of the key things we need to prove if we want to commercialize our powertrain, if we want to fly hydrogen and electric. Getting the operations right for the operator, but also for the airport operator is, of course, key. Now, the good thing is that hydrogen starts being used across several sectors, so that gives you opportunities to use that, and actually producing the hydrogen on site for an airport is quite an interesting opportunity to become basically their own fuel producers, if you will. You can balance your own power needs as well if you produce the hydrogen on site. And I think similarly we'll also see similar opportunities for the airports to take over more of that if we go hybrid or fully battery electric, if that were a thing.
It's a very interesting point, though, because it is one of the things that's high up on our agenda and trying to understand, which is why it's so important for us to have the OEM, Brit Norman, on board, who of course has access to all of the operators of the island, and to understand their mission profiles, to understand their operations, because an island of travelling from the coast to an island in Tahiti to drop off passengers at a luxury hotel is going to have a different operation to Loganair up in the Orkneys, where it is literally like a bus, and their turnaround times are 2 minutes. So it'll be interesting to explore where the operations can be flexible enough to allow electric aviation, but where then the trade-offs need to be between charging times, battery life, and the energy infrastructure as well. So, for example, how difficult or easy will it be to actually put a charging station that is fed purely by wind power on a remote island? It's very interesting, which is why we need to have the operators as key stakeholders.
Yeah, I think that compared to where we've been traditionally, I mean, in order to move to this into this new space, it isn't just about the people who've traditionally been involved, and that's, you know, we've got to bring all those people on board, the energy suppliers, the airports, the airframers, the operators. Everybody's got to be part of this if we're going to get to that optimum solution.
Good. Okay, so thank you very much for that. So the next question, which was very related to that, was what is ATI's approach to ensuring propulsion systems of the future are developed through much tighter integration with airframe providers? So a big part of that is ATI really bringing together people to actually ensure that we're getting well-balanced consortia which have end-user pull to actually drive some of those integration challenges. And in many cases, that's, well, typically that is what we see on all of our demonstrator programs today. So I think that that's probably answered that question. I don't think anybody else needs to chip in on that one. So we've talked a little bit about the timeline around hydrogen fuel cell infrastructure, which is a difficult question. There's another question related to that, which is about electrical power systems. So what does the panel think in terms of when electric motors, electric drives are really going to make a significant impact in the world of propulsion in commercial aerospace?
That's an interesting one, because what do you mean by
significant contribution?
Yeah. Because if it's coming from the thoughts about transatlantic flight, as in when is it really going to hit that? Who knows? Because it depends what fuel system that's using. To the point that's been discussed this morning. But if you are going to enable electric or hybrid electric flight in sub-regions, then potentially you're creating a market that doesn't currently exist. I've forgotten who it was who said this morning, why aren't we competing against trains? But was it Paul? He's absolutely right. You know, we should be looking at sub-regional being taking the lunch of the train industry, because we have so many airports around the UK, And if we are able to certify electric motors, power management systems, battery management systems to a point at which it can provide 9 to 19 seat commercial flight, then I would suggest that they will be contributing significantly to the aerospace industry by approximately 2024.
And adding to that, I think when we talk about significant impact, right, one thing is, yes, we can look at the numbers and we can say that, I don't know who had that earlier today in the presentation, that 2/3 of emissions are from wide-body aircraft or something like that, right? And so what are we even doing here? But the other really important, significant impact that we can have is on the public, just on the psychological effect, right? Showing people that we can fly zero emission. Like if you show people an ultra-high bypass, van, they will still see a traditional aircraft. But showing them something like a hybrid system, an all-electric system, maybe a fuel cell system even, people will see that it's possible to fly zero emission, and I think just the message sending that to the public is a significant impact, even if it's only going to cut actual emissions by, I don't remember the number that was mentioned there earlier, right? But I think kind of basically sub 600 mile travel has roughly 16 to 20% of worldwide emissions. That is a significant chunk, but it's not the 80%. But in the public mind, I think that's where we can have probably the biggest impact in the near term.
And electrification will have a role to play in terms of maybe augmentation or electrical units to help improve the efficiency of some of the larger engines as well. And so while we're not talking about the hybrid electric and all electric powertrains, there will be a role for electric components and electric systems in that market as well.
Very good. So my last question, which is just to kind of close this session down, is around the different types of energy that we can see in the world of propulsion. So the question is it a winner-takes-all race between biofuel, synthetic fuel, hydrogen and batteries? Can all take part of the prize, or is it something in between? What's going to happen? So
Get the crystal ball out.
yes.
I personally, I don't think it's an all or nothing for any particular technology. I think they'll all have their own application, and I think aviation and how aircraft are used differ so greatly depending on, as I said before, the mission profiles, and depending on what the operator's trying to do, that I think each will have its own pros and cons. So I think anybody who's looking at any technology that's going to be lower emissions we should be supporting them all, which is why we're working with Zero Avia as well, hedging our bets, some would say. But I think they'll all be successful, to be honest.
Yeah, it's certainly not a winner takes all.
No, I was gonna actually just second that, right? Like we will need sustainable aviation fuels if we want to solve this, if we want to actually get net zero, because you still have emissions in the air. But I do think whatever can be done, hydrogen electric, battery electric, or probably hybrid electric, will be done that, and that's a matter of economics as much as of emissions, I think. So that's just my point of view.
Great. Thank you very much for all of your questions, and certainly thank you very much for our panellists for their very vibrant delivery of their presentations and some good responses to the questions that you've asked. So thank you very much.